Please download the handouts from the Dropbox link, which is located in the chat feature at the bottom of your screen. Handouts include PDFs with slides for note-taking and other materials we'll reference during the presentations. We are recording these sessions and we'll make them available for you online. PCI has met the standards and requirements of the Registered Continuing Education Program. You must attend the entire presentation to receive the 2.5 personal development hours for this seminar. Credit earned on completion of this program will be reported to rcep.net. A certificate of completion will be issued to each participant. You will receive an email from RCEP within 7 to 10 days to download your certificate. Please know that permission from PCI is required to use any of the protected material delivered during the program. And now to get started with our presenters. As the Executive Director for the PCI Mid-Atlantic chapter, I provide technical and education support to DOTs, the design and construction community, and professors in their academic curriculum throughout New Jersey, Pennsylvania, Maryland, Delaware, Washington, D.C., and Virginia. Reid Castrodale and I share responsibility for the New York City market. There are 14 transportation producer members in the Mid-Atlantic chapter that deliver assistance, design assistance, budget development, schedule planning, plant tours, which you'll meet one of our producers here shortly, and he'll talk about that as well as give you an overview of a plant and other services to state DOTs and their engineering consultant partners. It is an absolute privilege to introduce Reid Castrodale and the rest of our presenters. For the past 30 years, Rita has provided leadership, support, and education to the New York City market, as well as to the rest of New York State, Connecticut, Rhode Island, Massachusetts, New Hampshire, Vermont, and Maine. Through her Bridge Technical Committee, countless resources, new products, and training seminars like this have been delivered in partnership with state DOTs and her regional producers. Reid Castrodale, president of Castrodale Engineering Consultants, is a structural engineering specialist in prestressed concrete, lightweight concrete, and accelerated bridge construction. He is a registered professional engineer in 3 states. Reid is the bridge consultant for our Georgia Carolinas PCI chapter. He is the managing technical editor of Aspire magazine and a fellow of PCI. He's been active in various PCI bridge committees for over 30 years. JP Binard is the owner of Precast Systems Engineering, PSE, which specializes in construction engineering, primarily focused on precast, prestressed concrete for buildings, marine structures, and bridges while utilizing ultra-high performance concrete in components and connections where possible. JP also chairs various PCI committees and has authored and co-authored several papers on UHPC and other precast, prestressed concrete topics. Greg Gorman is the Senior Vice President and Chief Operating Officer at Prestressed in Roaring Spring, Pennsylvania. Greg has 39 years of experience in the construction industry, with the 20 most recent years in the prestressed precast concrete sector at Prestressed and New Creek Products. A little bit about some of the handouts that you should see in the chat function at the Dropbox folder. PCI Mid-Atlantic and PCI Northeast have created easy-to-use, up-to-date transportation producer member product directories. In the Dropbox folder, you can download each of these files. Product categories, if you look to the upper right part of the screen here, you can see that in these matrices, there are the bridge products, piling, precast substructures, and other products such as sound walls, traffic barriers, and specialty products are on these directories. PCI recently published a new 2021 Transportation Publications and Online Resources Catalog. This 20-page reference guide, which is also located in your handouts, reviews the 20 publications and 28 online e-learning courses available for your professional use. During her session, Rita will discuss some of these specific publications and courses. For today's agenda, Reid Castrodale will discuss the basic concepts of prestressed concrete, fabrication of prestressed girders, and economical detail of prestressed girders. Notice that each one of these topics has a separate handout in your session 1 folder. Greg Gorman will deliver a virtual plant tour, and Reid Castrodale will provide an overview of transportation resources, including next beam updates. We'll conclude with a question and answer period facilitated by JP Binard and Reid Castrodale. Note that our sessions on Tuesday, April 20th and Tuesday, April 27th, the other two counterparts to this bridge design seminar, will cover different topics each session. Rita will provide a brief overview of each of these sessions during the wrap-up portion this afternoon. Now I'm going to turn it over to Reid, who's going to be in the basic concepts of pre-stressed concrete. Thank you again for joining us.
Thank you, Dawn. As I try to get things moving here, we'll start out. There we go. And thank you for the introduction, Dawn. And I'd like to thank both PCI Mid-Atlantic and PCI Northeast for sponsoring this seminar series. It's always exciting to get to do one of these and pass on some good information about pre-stressed concrete for bridge components. Just a little bit more background on things that I've been doing. Again, I'm Reid Castrodale. I'll give you a little bit of an introduction here. Let's see if I can change one other setting first. Okay. I've been giving seminars like this for about 25 years. Some of them have been in, a number of them have been in these regions. So some of you may have some familiarity with me. Back there 25 years ago or so, I was at the Portland Cement Association, and that was at the same time that the LRFD specs were rolling out. So we were doing how to design pre-stressed concrete with the LRFD. Then I also in the mid-90s, I was involved as the co-chair of the committee that developed the PCI bridge design manual. So I did some traveling and gave presentations on the manual as it was being introduced as well. So now I'm a structural engineering consultant, as Dawn mentioned, mostly with pre-stressed concrete, lightweight concrete, also with some ABC work. So I do a variety of different things. You see that one of them there is being the managing technical editor of Aspire magazine, the concrete bridge magazine. I hope you're familiar with it. If you're not, you need to be. Just got my new issue the other day. So hopefully you can see that and have your own copy. And I am the guy that you need to get in touch with if you have some good projects that you would like to offer as articles for Aspire magazine. So you can use my contact information there. One other thing I'd just note is that I went to Georgia Tech for my undergrad and University of Texas at Austin for my master's and PhD. And you can see a picture that I scanned out of, I guess, my dissertation, where I was testing pre-stressed concrete girder there at the lab at UT. Getting to see that, getting to test lightweight, or not lightweight, but pre-stressed concrete, building it ourselves really gave a good background in understanding how concrete behaves when it's pre-stressed. And with that, we'll go into pre-stressed concrete. Pre-stressed concrete, when we pre-stress it, it's really transforming concrete from a material that cracks into an elastic, uncracked material at service limit state. That's what the point typically is of why we pre-stress concrete. When we do that, it prevents the concrete from cracking at the limit state, at service limit state. It gives us the gross section properties. We maintain that for improved stiffness. And then it also provides an active force that closes flexural cracks so that we don't expose the reinforcement to corrosion with open cracks. So those are the main points. Another concept that's involved is that pre-stress forces within a member balance loads. We'll talk about that briefly in just a moment. So it's really an ideal combination for bridges. Pre-stressing allows longer or shallower spans, it improves durability, and it's a very adaptable concept. When we pre-stress concrete, we use high-strength steel, and that steel is pre-tensioned or pre-stressed And the reaction of that against the concrete then pre-compresses the concrete to counteract the tensile stresses and therefore eliminate cracking at the service limit state. We don't usually design by using the concept of balancing the pre-stress, but we can. For example, this top item here, if you look at it, this top element, perhaps this could be a transfer girder in a building where you have two concentrated loads coming down, or it could be loads from a straddled girder across traffic, and these would be reactions from bearings of pre-stressed girders. If you put a tendon in this case it would be post-tensioned, that is deflected at the points of load application, you get an upward force that is applied to the concrete by the pre-stressing that would then counteract some or all of the applied loads above. So that's what we're talking about by load balancing. Typically when we design, we just look at stresses, but this is an approach that can be very useful in some cases. If you have a circular or parabolic tendon profile, it exactly counteracts a uniformly applied load. Also, even if you have straight strands, you have a moment that's being applied that counteracts, not exactly, but it does counteract the applied loads. And then there are also options like this over here, where if you have a cantilever bent, where you have a heavy load on it from bridge girders or a box girder or something like that, you're going to have sustained tension on the back side, which would open cracks. If you apply a pre-stressing force here, typically using post-tensioning, which we'll see later, but if you put that force across this side, it pre-compresses that side of the element and you will not open those cracks. So in that case, that's a good example of a load balancing application. And let's see. When we pre-stress concrete, we are combining high strength steel with high performance concrete. We have to have high strength steel in order to do it. We have to have a significant amount of strain that we can put into the pre-stressing steel before we lock it off to the concrete. What happens here is we're showing a stress strain curve here. Stress versus strain. This is a typical stress strain curve for pre-stressing steel. We might jack our strands up to this stress, which is to a specific strain. As soon as we lock that off, if there's shortening in the concrete, either due to elastic shortening, shrinkage, creep, even thermal, we are going to lose some strain. When we lose strain in that steel, we're also going to lose stress because the strand will be coming down that stress strain curve. So that's why we want to have enough strain remaining after those losses that we can still have a significant pre-compression. Back years ago, people tried to use mild reinforcement to pre-stress, but you simply can't get enough strain into it without yielding the steel, which wouldn't do you any good. So that after that force is locked off, when you have creep, shrinkage, and elastic shortening, you'd lose most, if not all, of that pre-stress. So that's why we have to use high strength steel. There are two methods of applying pre-stress to an element. One is post-tensioning that you see here. When you have a post-tensioned element, you cast the concrete with some holes in it. Those holes are ducts. After the concrete hardens, typically you put strands through those ducts, and then those strands are tensioned with the reaction being applied against the concrete member. You have permanent anchorage hardware then that is used to transfer the force and maintain that elongation in the steel. And after you have locked up that elongation, applying that pre-stress to the element, the duct is typically grouted both for bond as well as for corrosion protection. And I might just point out, you see down here at the bottom, many figures in this session are from the PCI Bridge Design Manual. The black and white ones typically are from the Bridge Manual. And in this case, we have a couple of color images that are out of the introduction to the Bridge Manual. The second method for applying pre-stress to concrete is pre-tensioning. In this case, the strands are tensioned prior to placing the concrete. So you have to have an external device, structure, to maintain that elongation, to give you the reaction for that force. So you have abutments, or even perhaps the form itself, that reacts, provides the stiffness so that you can tension those strands. When the concrete then is placed around the strands, it hardens, it reaches the required initial or transfer strength. The force can then be transferred from the strands to the concrete, which pre-compresses the concrete. And in this case, the force is transferred to the concrete only by bond. There are no anchorages, no permanent anchorage hardware at all in the beam. And that's how we do it for pre-tensioned concrete. We these days use 7-wire strands for applying the pre-stress force. You see photographs of a couple of different sizes and even an epoxy coated strand here. 7-wire strands are standard. 6/10 diameter is pretty much the standard of what we're using nowadays, although 7/10 strand is being studied. We also have some corrosion resistant options of stainless steel, carbon fiber, and even epoxy coated strands for corrosion resistance. Typically, we use grade 270 strands that have 270 KSI guaranteed ultimate tensile strength. As you see here, the stress strain curve doesn't have a sharp knee in it, so there's no defined yield point, and we use a 0.2% offset, or in this case, for grade 270 strands, we get a yield at 243 KSI. We now do have available in the marketplace grade 300 strands, so that can also be used. It's just hitting the market. When you post-tension a member, you have to have hardware, and this is probably the last mention we have of post-tensioning, other than some combinations with pre-tensioning. But you have to have a hardware, a device that's embedded in the concrete that distributes the force through the concrete or into the concrete, since it's a highly concentrated, large force that's being applied with all these strands. Here's an example of a slab tendon, 4 strands that are in a flat duct that's going across the top flange of a segmental box girder or just a bridge deck. This is a more typical multi-strand tendon that's used in spliced girders or something like that. And then we also do have some bar tendons that are available. We wouldn't use those in girders, but they can be used in other applications where this is higher strength than a normal bar. And you can accomplish pre-stressing with it. When we pre-tension beams, here's some examples of them where the strands are just sticking out of the ends of the beams after they've been cast. They've been, in this case, they're still sticking out. Over here, the strands have been cut off. These are rebar that are still extended. You can see here as well that the strands are sticking out, and then usually they're cut back flush or burned into the concrete and then sealed off. And this is a next beam. If we compare reinforced and pre-stressed concrete behavior at service limit state, with reinforced concrete, as we all know, it's a cracked section. So the top of the member, flexural member, would be in compression down to the neutral axis. Below that, we would neglect any tensile capacity of the concrete. And the only thing that's available to provide that balancing force for the compression is the reinforcement, the mild reinforcement. For pre-stressed concrete, we have an uncracked section at service limit state. And while we may have a little bit of tension, it's not enough to crack the section. So we're able to use gross section stiffness, which is good for deflection and such. At the strength limit state, the behavior between the two is essentially the same. The reinforcement does yield if you're using mild reinforcement, while with strands, they're past yield, and we have to estimate the stress in the strands, which is nearing the strength. The compression stress block's the same for either reinforced concrete or pre-stressed concrete. So why do we pre-stress? We pre-stress basically to get structural efficiency, cost effectiveness. We're increasing spans, reducing the number of girders, whatever it may be, and then durability. We're getting that crack control that we want. And we also have a high quality concrete from a precast plant. So those are the main benefits, but there are other aspects of design that are important. Low maintenance, we have the quality, we have standardized section to get the greatest economy out of these cross sections. It's a good clean look. We can accelerate the bridge construction. They also have good fire performance. The concrete protects the steel within, and pre-stressed concrete has performed well over many years. The first pre-stressed girder in the US was introduced in 1949. It was actually cast on the site, and post-tensioning was used with wires. Since 7-wire strand hadn't yet been developed, this is the Walnut Lane Memorial Bridge in Philadelphia. It sparked a lot of interest. There was a great deal of publicity about it. Articles were published. Really sparked the emergence of pre-stressed concrete in the US. Now, there were some difficulties with this early post-tensioning system and the effectiveness of grouting and such, but it was replaced. The bridge was replaced with pretty similar current sections back in 1990, and there are a number of articles both about the first bridge and the replacement bridge, as you see in the PCI journal there. At that point, there was rapid development of the technology and materials used for pre-stressed concrete. In the 1950s, 7-wire strand was developed. Plants with long line pre-tensioning beds were developed. Chemical admixtures, higher strength, steam curing, all of those contributed to the rapid development and use of pre-stressed concrete in this era when the interstates were being built. So by 1958, there were more than 200 pre-stressed plants in the US. So from nothing at 1950 to 200 plants by 1958 is really a significant growth. As the industry was developing, they recognized the need to focus on quality, and they developed a plant certification program. It's been in place since 1967, and it really assures owners, specifiers, designers that plants have the capabilities and the processes to really produce a quality product. Certification programs are also there for plant personnel. Many of the DOTs in the US require PCI certification. It's up to just over 80% at this point of the DOTs, and most in the regions that we're talking about today are also requiring PCI certification for pre-stressed girders. Quality control, as I've already mentioned, is very important. There's a lot of inspection. Using plant cast concrete gives a great opportunity for all this inspection. And also, pre-stressed members are essentially load tested at transfer of pre-stress. That gives a real good indication of the quality. So how much or how widely used is pre-stressed concrete? The National Bridge Inventory, which is used by FHWA and maintained by them, has the inventory of all states, all bridges in all states. You can look at that and get some very good information that helps us to understand. It's not perfect, but it gives us a good indication of the use of different materials for bridges. You see here a plot of the materials, four materials. We see there's pre-stress in the light blue, reinforced concrete in the yellowish orange, steel is red, and timber is the green line down here. So by year, and this is by year that the bridge was built, you're seeing a comparison of how many bridges have been built during this particular year. So you can see out here by the end of the data, this is a particular set of data that was provided by FHWA. They don't provide it in this particular format any longer. So the data stops at 2013, but you can see that nearly 50% of the bridges are pre-stressed concrete. And pre-stress is the only product that has gone up over this period since 1950. All the others have gone down. I have taken a look at something, if you are not aware of it, the FHWA Info Bridge portal is a great way to take a look at data from the NBI about bridges across the country. There's been 2 articles in the Aspire magazine that could be helpful for looking at that. But at any rate, looking at the most recent data, last 5-year period, we're seeing the same sort of relationships that are shown here in this figure. Something else we can get out of the NBI is information on what we used to call structurally deficient bridges. It's just poor quality bridges, poor performing, perhaps. I'm not quite sure what I'm supposed to use after poor, but it's the equivalent to what we used to call structurally deficient bridges. And you can take a look by material. Here you can see that taking a look at 2015 data, 3% of pre-stressed concrete bridges were rated as structurally deficient, 6% of reinforced concrete, and then it went up from there. So pre-stressed concrete has done very well as far as durability over the years. Last thing I'll talk about for this particular part of the presentation is that the PCI Bridge Design Manual is a very important document. If you don't have a copy, you should. If we were doing this live, I'd have people raise their hands. How many people have a copy of the PCI Bridge Design Manual on their shelf or in their computer? It has a lot of information about design of pre-stressed concrete. We developed it back in the 90s. We didn't have this sort of thing, so we just really saw a need for it. And through a great deal of effort on the part of PCI and a great team of authors, it's been developed and maintained ever since. So it has design procedures, design aids, great design examples, and then discussion of different applications and special topics. One of the most important things is in chapter 3, which is about fabrication. And I'll get into that stuff in the next presentation. This used to cost a couple $100, but it is now free from PCI, and you can download it from the bookstore. So with that, that completes the first of our presentations here, and I will move on to the second one, which I am also doing, and talk about fabrication, essentially talking about what's in chapter 3 of the bridge manual. Oops, I got 2 slides there. Economical fabrication of pre-stressed concrete bridge girders is really dependent on us as designers designing properly and then providing good details. For the most part, we have good details that have been developed over the years, and that's good to use those. We want standardization. That's important. So that's part of the reason that we're doing this presentation, is so that designers will understand how girders are fabricated and maybe understand some of the reasons or some of the details that could help us out when we're fabricating girders in order to get the most economical solutions. Much of the information that I'm going to be using comes out of the PCI Bridge Design Manual. You see the 3 chapters here that I'll mostly be focusing on. And there's quite a range of details. I'm just looking at a few of them. Greg Gorman in the next presentation will show you a few others, some similar and some different, but at any rate, some opportunities for the fabricators to do their own thing. So we'll get right into it from here. Here are 4 plants. These are just examples of plants. 2 of them are in Pennsylvania, one's New Jersey, one's Virginia. They're somewhat typical of plants all across the country. They may have indoor fabrication facilities, as shown here. There's an indoor facility, an indoor pre-stress line, and then everything else out here is storage. This plant has outdoor pre-stressed beds. So things vary from region to region and plant to plant, but they are large manufacturing facilities. They have good quality control and they control their processes, and they are certified by PCI. To make the girders, we use 3 materials. You see these here. We'll have another brief discussion of those materials. Again, 7-wire strand, grade 270. The strand comes shipped in coils that you can see here. And then they're placed, strung on the bed. And here you can see a unique situation where this is a spliced girder that's being fabricated in a plant. You see both pretension strands, which are the circled in red, but you also see the detail spiral and the anchorage and the ducts for post-tension tendons that will be installed after the girder has been fabricated and sent to the and erected in place. So that you can combine pretensioning and post-tensioning. There's no reason we can't. They are both pre-stressing the concrete to accomplish whatever purposes we have for that. Mild reinforcement is used in the girders. We have stirrups, we have confinement steel, which is enclosing the strands at the ends of the beams here. That's confinement steel. And then there's typically some steel in the large wide top flanges that are in the girders. You see 2 examples here where you have stirrups and stirrups here out near midspan. There's a hole down there, so we're in the midspan region. And here's the end of a girder where there's a lot more steel, a lot of congestion, some horizontal steel as well. We have to think as designers about, can we really get all of that in there? But we'll talk about that more in a little while. The concrete that we put in here is just a high performance concrete, typically high strength, can be up to 10 KSI. We don't usually want to just go to 10 KSI unless we need it. The higher the strength, the more of a challenge it can be for pre-stressors to fabricate that mix. We do want a high flow mix in order to get that concrete to move through all that congestion of reinforcement and strands, because we have to be able to get the entire form filled up. So the high flow mixes are important. We also want a rapid strength gain so that the girders can be taken out of the forms and get them off the bed so you can start making another set of girders. That's how we get efficient production in a pre-stress plant, is to turn those beds over and use them as frequently as possible. So here's just some examples, just like a regular batch plant that's located usually on the plant property. So aggregate going up the conveyor goes up into the mixture, and then it gets discharged into a delivery vehicle of some sort. So now we'll talk about fabrication. And each of these topics will be discussed as we go along. And we'll start out by talking about forms. A number of different types of forms. Oftentimes we don't have to think about that as a designer, but we should be aware of them. So we have external forms. This is typical. You have a girder side form shown here. Here you can see the form. These are supports here, so the side form rests upon these supports, and then you can't see it very well, but there's some blue things that are tying the bottoms of those forms together underneath the soffit. So here's the reinforcement in place, and the forms are going in place so that they can then cast the concrete. Box beams are also fabricated using the same thing, typically with a removable side form. And we'll talk a little bit about that later. There are some other types of forms that can be involved. We can have adjustable forms. Here you can see a top flange on a bulb T, and then there's another chunk of form that's been attached to that to shorten or narrow the top flange. Maybe it's a highly super elevated bridge, So with a high super elevation, you get a lot of haunch or buildup over the top of that wide top flange. So in this case, it's been formed back. So it's a narrower top flange. That's just attached to the form, and it can be removed when you want to go back to using the full top flange width. Another thing is that our standard girders these days typically have the same bottom and top flange configurations. So it is possible to fabricate the forms with fillers. So you can take one top and one bottom form and then use it for a whole family of heights of girders by inserting these filler pieces. Another option is, in this case, this is a form, side form for fabricating a pier segment for a spliced girder bridge. This is actually a segmented form where the top part is a typical bulb T form, and then a special bottom has been spliced onto that top form to give you that segment form without having to come up with a new, totally new form. So those are the side forms. Now we need to go to the bottom form. You have to be able to form the bottom of the girder as well. So this is a soffit form that you can see attached to these supports. It defines the width of the bottom flange. It's supported above the ground by these supports, and it's attached to those supports so it doesn't move around. You can see a different way of doing it here. So just some examples. So that's the soffit form. So that's three sides, the top and the bottom, and each side, or the sides and the bottom of the girders are formed. We have to confine the ends too. We have to provide a header, it's called, to end the girder. So that's a form that's applied at the end. Here's a stack of headers that are waiting for use. Here's a wooden header that's been installed at the end of a girder. Here are some steel headers that have been installed. The strands are passing through them. And then the rest of the reinforcement will be tied around it. Here, excuse me, here is a header that has been modified because it's on a skew. So we aren't going to typically use a steel header for a skewed girder, but we can use perhaps a steel header behind it to provide support for it. And then there's a wooden form that's constructed from that provides the skew on the end. So end forms are called these headers. And if you are draping and raising strands through the section, these headers have to be slotted. You can see the slots over here in these sections, headers. There are also some sections that are voided. They don't have concrete in the middle. It's been removed in order to lighten the concrete. Voided slabs or cord slabs are typical of that. You see an illustration in a photo from the bridge design manual here. Waxed cardboard void forms are often used for that. Here you can see some in place, tied up in the forms. And polystyrene foam can also be used either for, this is a trapezoidal box beam that was built, I think, in New York State, must be over 20 years ago now. But those are also used rectangular voids for box girders these days. You can have removable internal forms, but the point you have to remember there is the hole has to go all the way through the section, and rarely do we see that in highway work. This is a railroad bridge box girder that's being fabricated here that uses a collapsible interior void. Something else that we sometimes see that's fabricated using a collapsible void is a cylinder pile, where this pile can retract upon itself so that it can then be extracted from the pile after fabrication. In some cases, forms are self-stressing. As we mentioned earlier, for pre-tensioned concrete, you have to be able to pull the strands before the concrete is there. So in this case, the formwork itself can be used. This is a double T form. It's similar to an X beam. And these elements have a draft, a taper cast into them so that they can be fixed side forms. So in that case, you can just lift the product out of the forms. So the forms are always there in one piece, connected into one long piece. And in that case, that gives the reaction for the pre-stressing steel. So you can see the strands here at the end of the beam that are anchored. Here's a square piling form. Oftentimes you'll see them here on a quad form where you'll have 4 lines that are cast at the same time. You see the strands anchored just against plates that are then bearing against the formwork itself. And I might just back up on this. One caveat here, this is a building product here, and we don't typically drape strands for a next beam. Just a thought to remember. For the pre-stressed beds, we have to have the anchors at the ends, these abutments at the ends. That's typically what's done. If we don't have a self-stressing form, instead we have side forms that are moved on and off and segmented, so there's no way that they can really function typically as a form that would resist the pre-stress. So instead we have a structure at each end, abutments, and these abutments are fixed into the foundations. The slab may function as a strut between the abutments, and these beds can get quite long. They can get up to 500 feet long, maybe even longer than that. And in some cases, they can also be short. And it all depends on the types of products that are being manufactured. Here are some examples of the abutments, these big chunks of steel coming up out of the ground. Here's another piece coming up, and this one's actually a tied or strutted abutment, where this is tied back so this steel doesn't have to take all of the force in bending. But these cantilevers by themselves are typically the ones that are used in most plants. Once in a while, you may need to use a different kinds of a bed. So here's not a long bed type structure. This one is used for casting something like a pier segment for a spliced girder, in which case you have a significant pre-stress, pre-tensioning force that's located in the top flange, because this is a negative moment element. So the reaction for the pre-stress needs to be up in the air. So that is done here. These are actually pieces of concrete piling that have been placed here up in the air. A structure is placed between them. Strands are then stressed between them, and the forms are placed between these struts. And that way we can get this high amount of pre-tensioning in the top of the section. So that's called a strutted bed. You don't always have to have it way up in the air. You can use them for other types of sections also. Once you get those abutments in place, you have to span between the abutments in some way to provide anchorages for the strands. So that's the anchor plate. You see here a couple of different types of anchor plates. You see that they're fabricated out of a stack of plates in many cases here. So these plates are spanning across between the abutments, and they're spaced out so that the strands are placed between them. So typically we have 2-inch strand patterns. So these plates are centered 2 inches apart. That gives a gap for the strands to fit through those plates and be anchored on the back side. So you can see that here. Here are the strand anchorages. So those hold the strands in place while the concrete is being cast. These any of these can actually be adjusted in location typically, but we like to keep them as standard as possible and have especially the bottom straight strands to be in the same location would be helpful for the fabricators. Here's a self-stressing piling form, and the strand anchor plate is just a drilled plate thick plate that's placed on the end of the form, and the strands are passed through it, and these are the chucks that hold it. I've talked about chucks a couple of times. When you pull the strand, you have to lock that elongation off in some way. So strand chucks are used for that. This is what we see here. It's a reusable type of a chuck. Unfortunately, since we're not live, I can't put one of these up at the front and you can come by and take a look at it at break. But it's a barrel that's tapered, has a tapered recess in it. There are wedges, 3 wedges typically, that are held together by an O-ring the strand passes through, and then there's a cap that's spring loaded that connects into that. We sometimes may use a single use strand anchor. Here you can see that's a multi-use, and this is single use. It only has 2 wedges, and it's a little short barrel. Those aren't typically used in production. They may have other special uses. And then there's also the potential for using strand splices. Now, you don't put these within members. This would be if you had tails that you wanted to use for stressing. Maybe you had a lot of unused space in a bed and you were going to have to do that several times. It's possible that you can use strand splices to minimize the use or the waste of strands in situations like that. Usually we single strand tension the strands that are in the girders. This is one way to do it. Here you can see a single strand jack. That's what this thing is. It's a hydraulic jack that pulls one at a time. So it has a long travel on it. They measure the elongations, and then that elongation is compared with a computed elongation based on the force that would be in the strand. So you have the pressure gauge on the pump and you have the elongation. You can compare the numbers that you would get using those 2 inputs and make sure that you have readings that agree within 5%. So we're getting good control over force in those strands. Elongations, just in case you're wondering, say for a 500-foot bed, it could be 42.5 inches. That would be a typical elongation. So you have to have a lot of travel in that ram, or else you have to do it in stages. There's also a concept called multi-strand tensioning and detensioning, in which the abutment is in the center of the stressing arrangement. And then you have the strand anchor plates that slide over on the girder side of the abutment. And then you have the ram on the back side of the abutment, and the ram pushes on another plate. So there are a couple of large bolts or rods that pass from this side through the abutment and to the other side. And then all the stressing of all strands is done at the same time. So that's a gang tensioning. Here you can see an example. Here's the abutment. Here's the bottom strand anchor plates, the top strand anchor plates for the draped strands, and they pass to the other side of the abutment to a single large ram at the top, and then 2 even bigger rams that are at the bottom that would pull those strands. Now, when you pull those strands, you have to lock them off, lock the elongation off. You don't maintain that elongation using the rams in case you had a leak or something. So those get locked off mechanically with some nuts on these big rods. And then to detension, you simply re-energize, repressurize these rams, loosen those nuts, and then detension the whole bed at the same time. We can have straight strands in our beds. You can see straight strands here. Or we can have draped strands. Draped strands have to be held down. They don't just stay put because you told them to. So you have to have a piece of hardware that's cast into the girder that has rollers on it, low friction rollers, so that the strands pass through those rollers and up to the end of the girder and anchorages. In this case, it's a split anchorage, a split hold down, because there are so many strands. There are capacities that are related to each of these hold downs, and you can only hold down so many strands, but you can use multiple hold downs to accomplish the job if you need that. Here you can see that we have to have some hardware under the bed that actually engages the rod that's coming out of this hold down and holds it down. You have to have a reaction here. So there's a plate that's cast into the bottom of the bed, then devices that straddle that plate with a pin going through them. And then here's an anchor that's the nut that's going up through the soffit and to the hold down device. Here's another example. You can see a pin going through, and here you can see this is a standoff above the soffit that's bolted into the hold down. So this is a bolt here. There's actually a pin at this point that allows the anchor to rotate, so it's not putting moment into that pin or the hold down. And if you have a hold down, you have to have a hold up. So outside the girders, you'll have a hold up device. In this case, it's supported by an A-frame. So the strands go through there and back through some more rollers and then on to being stressed at this end. We can also use some sorts of devices like this that are hold down or hold up devices that actually sit within the forms. You can see lots of rollers here. So it's an internal device and it actually bears on the pallet. So you have to make sure that the pallet can stay. We don't have to, the fabricators do. Here's some close-up pictures of one plant's internal hold-up devices. This is in the bottom, or in the lowered position. You can see rollers down here. And then the crane would come in. Once it's put in position, the crane comes in and it lifts up this bar with all these holes in it. And then a guy gets up there and sticks a pin between or into one of these holes to maintain the elevation of those strands. And usually those are typically under tension when they're pulled up. So it's has some safety issues involved as the guy's right next to strands that are live, that are being tensioned while he's putting the pin in. So there are safety considerations we'll talk about later. But here you can see the strand rollers are up in the elevated position. When we stress strands in a plant, all the strands are tensioned in 2 steps. You put an initial tension into the strands, depends on the bend length and procedures and such. That takes out the slack. It seats the chucks at the dead end. The dead end is the end you're not stressing from. And it really gives you a good, reliable, consistent starting point for making your elongation readings. So then after that is established, you apply the remaining stress up to the full tension, which is typically 43.9 kips for a 6/10 inch diameter grade 270 strand. There may be some corrections that would be applied to the elongation in order to account for things like the abutment moving or the chucks seating or temperature, because as temperature changes, the strands are going to elongate or shorten. And the draped strands, if you raise them after they've been tensioned, they're going to have different forces in them because, well, we'll talk about that a little bit more in a moment, but the forces and the elongations are going to be different for draped strands, which not only do you have safety issues with draped strands, you also have additional complexity in the stressing operation with draped strands. The other option we have for dealing with stresses at the ends, and I'll talk about that in a later discussion. I think that's that's a week from today. We'll talk in much more detail about draping and debonding. We can also use debonding in order to control stresses at the ends. And what a debonding situation does is the sleeve over the strand, which prevents the bond between the strand and the concrete. And if you remember, for pre-tension concrete, that's how we transfer force between the strand and the concrete. So many of the producers prefer using straight strands and debonding rather than draping, as for the reasons I've already mentioned. And you can also, in some cases, use debonding for top strands in the center portion of a girder. And I think we'll talk about that tomorrow in the debonding discussion. But the debonding has to be applied to the strands. So they have to be able to access those strands. We as designers don't have a whole lot to figure out about that in the shop drawings. If we put some in a place that a pre-stressor might not really like, they can move those around in the shop drawings, and hopefully we'll approve those. Another thing that we have to remember is that those sleeves are applied on the strands and they have to be sealed. The whole point is that you don't want concrete to get to those strands in the debonded length. So the ends of the sleeves have to be sealed, both ends, the end that's up against the header, as well as the end that's up into the beam. Those have to be sealed to keep concrete from getting in order to have effective debonding. There are a couple of materials that are used. There's a two-piece snap together type of debonding that's used. Also, a solid tube can be used, although you have to thread that through. The strand has to be threaded through the debonding as it's placed in the bed. So it's not as easy to install as just being able to snap these things around the strand. Split sleeves have been used. It's one piece of plastic that curls around on itself. So it's pretty easy to get onto the strand, but it does have to be taped for its full length to prevent any concrete from entering the sleeve. I don't know if you can really see it very easily over here, but I tried to cut a piece of this debonding on a spiral so you can get an idea of how it overlaps. So it's wrapped around the strand, taped, and then it has to be sealed at the ends as well. If the sheath is not continuous, for example, this yellow material comes in certain lengths, like 8-foot lengths. So if you have a 12-foot debond, you have a joint that's in the middle of the debond. So you have to tape that as well. Again, the whole thing we have to think about with the debonding is during fabrication, concrete can't get to those strands to start bonding. So for an economical design, we really need to understand as designers just how the girders are manufactured. So we want to provide a minimum debond length. We don't just want to say, well, 15 feet must be good, let's give 25 feet. That's going to affect the cost, it affects labor, and it also affects the stress condition. So you should provide the minimum debond length that's required. If you have a lot of debonding, you need to stagger terminations. The specifications deal with that. It's similar to cutting off rebar all at the same location. You typically don't want to do that just to avoid some potential for cracking. And we can consider access when selecting debond strand locations. If you have questions, discuss with your local fabricator. Give them a call and say, hey, I'm laying out some debonded strands. Do you have any comments on this? Or they'll do that when they get to the shop drawing stage. There are some other things that get put into a girder. We have bearing plates that are used by many states. We oftentimes have diaphragm holes or other types of inserts. And that's just something to be aware of. If we put on the plans that I want a diaphragm hole at this location, it's not going to stay there by itself. So the fabricator has to add in some detail bars to hold this hole form in the right position when we're pouring concrete around it, and the concrete's going to try to push it around. So we need to be aware of that. We don't have to detail them, That'll come in on the shop drawings, but just be aware that that sort of thing will show up. And then we also see, for example, a bearing plate that's in place down here. Those usually have to be put in before the strands, because once those strands are tensioned, there's no way you're going to get a tall stud between those strands. Occasionally, we'll also see form and pipe hangers, as shown over here. This is coming out of the bridge manual. And it's just an embedment that's used either in the deck or the girders. But anytime you are putting an embedment in a pre-stressed girder and it's attached to the forms, that means they have to drill a hole through that form in order to attach that embedment. It can be repaired. It's done all the time, but just bear that in mind. As far as quality control, as they set up the beds, there's lots of opportunity to make sure that things are done right. So they can go and measure them, check the cross-section dimensions, and make sure that everything's being fabricated as they would like it to be. All the bars are in place. The QC personnel at a plant will typically develop the mixes, submit them for approval, and then implement the mixes and do the concrete testing at the time that it's getting used. They'll do the testing as well later for the hardened concrete. The concrete, once it's been batched, is delivered to the girders in different ways. This is one example shown here. Tucker built kind of equipment that has a screw auger that goes up through this. It takes the concrete from the tank here and up the auger and delivers it into the forms. This particular one doesn't agitate the concrete. It just sits in that tank. If you had like a ready mix truck that's used in some plants, that can be done as well, or overhead cranes. There are a lot of different ways to get the concrete to the forms, and the producers are used to making that happen in an efficient manner. Once the concrete gets in the forms, it needs to be consolidated. Typically, we use vibration, self-consolidating concrete, SCC, or high slump concrete's often used in order to facilitate the concrete getting in around all that rebar that we put in there and other embedments and such. We can use internal vibration that's placed from above, or there are also form vibrators. There's a track that runs along this girder form that's attached to that form. And then there's a device that slides in that track that is a vibrator right here. So they slide that along the form as the concrete is placed. Once the concrete's in the form, they need to strike it off, get it level across the top of the form, and typically it receives some sort of a finish to give some roughness for bonding a composite slab on the top. It's possible that it may not have a composite slab. For some cord slabs or box girders, it may just need a broom finish. Also, in some cases, the roughening may only be partial width. You can see that here in this picture. There are clips that are installed on the edge of the concrete right here. This is the edge of the top flange. These are for putting metal stay in place form angles here at the edges. So this will be covered up. This area will be covered up by the formwork. So there, well, I guess it won't be, but it's close. You don't need the roughening, the full width of these girders necessarily. So they've only had to roughen between the stirrups that are poking up out of the edge here. That's a good thing to think about. We usually have so much more horizontal shear capacity that we don't have to have it all the way to the edge. Curing is important. We typically get the concrete in the forms, get it finished, and then cover it up. In cold climates, they may end up using heat, applied heat in some way, steam. Some people have heating elements that are installed on the forms. So accelerating the curing using an elevated temperature can be used. And here's just an example out of the bridge manual where this is a typical cure used, time versus temperature curve for accelerated curing. After the concrete gains adequate strength, the initial concrete strength, FPCI, we can then detension those strands, and the force will be transferred from the abutments into the concrete elements to pre-stress the elements. So up to this point, the concrete is not pre-stressed. It's just reinforced. So you take off the curing blankets and then you start detensioning. If you're in a situation where you single strand tension, you'll probably single strand detention. And what goes on here is you can see this bed where there are a lot of girders down the bed, several of them, and then you see these people in between each girder. So they are cutting the same strand at the same time all down the length of the bed. So they have people at each of those stations and they know which strand is next, and then they come in and they detension that strand. Now the strands are heated until the wires relax and break. You don't go in there and see how fast you can burn through a strand. You're detensioning those strands to reduce the shock, the energy release that occurs when the strands do end up breaking. If you just cut them, that's high shock that can affect transfer and development lengths. So there's a specified pattern. You also have to release the hold downs to avoid the damage, as the girders will camber. The whole point is when you're putting pre-stress into the girder, it's going to start cambering. So it's going to try to raise up off the bed, and if it's still held down with the hold downs, that's putting more load on the girder and the hold downs. When you gang detention, as I mentioned earlier, you repressurize the rams, release the hold down hardware. You have to do that in this case because the girders are actually going to move down the bed as they are detensioned, because all of the movement is coming from one end. If you're doing it between each girder, then each girder's shortening by itself pretty much in place. As we are detensioning, as I mentioned, the girders will camber up. The ends are going to slide because the girder is starting to shorten. Oftentimes they'll make initial camber measurements while the girders are still sitting on the bed. That's pretty easy. You can just go out there with a tape and measure how far it is up above the bed. In some cases, fabricators will lift one end of the girder and then set it back down before taking the camber reading because the girder has some drag. It's been sliding as it's shortening. So it may actually have a little bit of that camber that's restrained by this sliding effect at the ends. Also, sliding of the girders in the bed can cause spalling at the ends. That's one of the good reasons to have bearing plates at the ends of a beam. It is an expense, but it does prevent spalling. It's probably the most fail-proof way to keep spalling from the ends of the beams. And especially if you have a skewed end on a bottom flange, that can be real problematic. You can sort of introduce twist into the girders if the skew goes all the way to the end. So it's generally recommended to try to keep the skewed ends. For skewed girders, you keep the bottom flange square and you only skew the top flange. We'll see a detail on that after a while. So once the girders come out of the bed, then we need to finish the girder ends. So the strands are sticking out of the girder, as you can see here. They're pre-tensioned, so these strands are sticking out. We don't want that in the field, so they cut those off. As we saw earlier, the same sort of picture. The strands are burned off. In this case, there's some short projections that are left because, as we can see from the rebar sticking out, this is going to be encased in a continuity diaphragm for continuous for live load design. So those are going to be encased, so there's no need to burn these off flush and seal them. Here's some girder ends that are at an expansion joint. So they have been cut off flush, sealed with epoxy at the ends so that the water that may come down through the joint if the joint fails will not be able to penetrate into the girders. Oftentimes what's done is that some sort of a recess is provided around the strands, usually with some sort of a foam like you see here, so that the strands can be burned back from the surface of the concrete, and then a patching material can be placed in there, an epoxy, to keep moisture from reaching those strands. After the girders are cast, there's also going to be a quality control check. You go back through, make sure everything's as it's supposed to be. They'll put some a stamp or some templates to indicate what this piece is and what project it goes with. And it's interesting, it's just a little item of note. North Carolina DOT has begun using RFID tags that are embedded in their girders, in the surface of the girder, so they can actually be scanned either visually by just taking the number off of that tag, or using the QR code that's on there, or there's also an electronic item in there that it doesn't have intelligence other than it just identifies what that girder is. So you can scan it with a radio frequency scanner to identify that girder. And they are keeping track of all of the properties of that girder in a file that's related to that girder number, so that at any point in time after it's been fabricated, if it's in the plant, if it's being shipped, if it's being erected, or if it's years down the road, they can still go back and access the information and identify that particular girder. On occasion, we do have some issues that arise during fabrication of girders. PCI has a repair manual, and we'll hear a little bit about that on the third day of our seminar from the author of the revisions of that manual, which is JP Binard. He's also on the call today. So this is an outstanding manual that gives a lot of good information that can be used to provide good repairs to girders that may have suffered a little bit of damage or flaws as they've been fabricated, because that can be repaired and used. Once the girder has been finished and coming out of the bed, it gets handled. Well, if it's just coming out of the bed, it has to be handled. It goes to storage, and then it's handled again to put it onto the truck. So we'll talk a little bit about that, and there is good discussion of that in the PCI bridge manual. We have to lift those girders somehow. So typically what's done is that you have strand loops. That's what you see here and here. That's multiple strands that are put together. They're run through a conduit that is then crimped around them. You can see that here a little bit. So that maintains the integrity of that group of strands. You can then lift those girders using those loops. The strands run typically down close to the bottom of the girder somewhere. Sometimes they're splayed out so that you get better bond. And that gives an adequate capacity for lifting those girders. Those are not in the plans. Those are things that are done by the pre-stressor. Having a problem here getting it to move ahead. There we go. There are also some other devices that can be used. Rigid connections. You can see here, these are actually stiff bars that pass through the top flange and are connected at a pin in the web, and then they go up to pins up above. So you can lift those girders. These rigid connections give additional lateral stability. You can also use slings. If the lifting loops aren't where you want them to be, perhaps, you can lift one end using a loop, block it up, and pass a sling underneath it, and then lift it using that sling. That also gives you some good stability. We also store our product in the plants. unless somebody's really eager to get the girders, but typically the girders or panels, as you see here, they're stored in the girder in the plant. There are approaches to doing that appropriately. You have to have dunnage that's adequate to keep them level so that they don't tilt. So here's some girders on dunnage typically, and some panels, and actually they're like stickers in lumber stacking. You have some other pieces of wood there, but it's important here that all of these support lines be lined up so that you don't introduce any bending into the members. So then we ship them. You pick those girders up and put them on a truck. It's a specialized equipment that's being used. Here you can see what it looks like. It perhaps as it's traveling to the plant, or arrives at the plant, where the rear axles are hooked up to the front axles for just driving back to the plant. But here you can see them spread apart. They're the rear axles. Here are the front axles that are attached to the tractor. Those rear axles are remotely steered. I always figure they must have some superhumans that have eyes in the back of their head or coming out their ears or something so that they can watch the back of the girder as well as look ahead and steer. But they do it somehow. They have a remote control up here in the cab, and they run what's going on back here. On a few occasions, they'll actually have a driver that's sitting down here below the girder. But you can see that the rear does indeed steer. Those axles are turned so that they can maneuver the girders to get them where they need to be. This is one of the longest girders that's ever been fabricated. That's up in Canada, but we'll talk about that in a moment too. There are a number of shipping considerations that need to be noted. Not so much by us as designers, although we really should be considering some of this to make sure that we don't have some stability problems. Typically, the fabricators are going to have an overhang between the end of the girder to the support point where they're being supported for hauling. That gives you greater stability, and it shortens the rig. So usually they have the full concrete strength by this time. And then there are a number of different approaches to tying those girders down. You can just throw a chain over the top with some protection on that top flange. Here's another one that's just chained over the top, but you also see there's a chain coming down that's going through an insert in the web, maybe a diaphragm hole. Here's a situation where the chains are going through the web, or perhaps hooked to some sort of a device that goes over the top of the web, allowing them to be tied down without going over the top flange. Again, those are details that the fabricator will work out with their hauler. There are considerations about shipping. We can, and some producers have, fabricated girders that then are having a problem getting a permit to get out of the plant. So that has to be considered at some point in the design process. Also, the length of the girder has to be considered for curves and obstacles. The shippers are used to doing that kind of evaluation. There are other factors that are involved here, as you can see, and we'll talk about those more when the discussion about lateral stability comes up on the third day. Access to the site is also important. So if you, while you are designing a girder, have questions about shipping, handling, stability, that sort of thing, please call the fabricator and talk to them, and they can get in touch with their shippers if it's a different entity. So that can be worked out to make sure you have something that can be delivered once it's fabricated. This is that same girder that we saw earlier. It was the record length. It was 210 feet long, 110 inches tall. It was an NU girder, 2,800 millimeters. Here you can see it loaded up. Here you can see that back dolly that's being turned to steer. So that was a long girder. but we now have a longer girder. We've had a couple that have been around the same length as that other one. It was in Canada, so we let them have that record. But we now have the North American record in the US. Washington State has a 100-inch deep girder that's 223 feet long along the center line. The thing has a wicked skew, 7-foot additional length due to the skew. If you go from point to point, it's 230 feet long. Lightweight concrete was actually used on this long girder in order to allow shipping, even though they only had to haul it like 7 miles or something like that, or maybe even less than that. There is an article on the fall issue of Aspire that discusses the fabrication of this girder. You can also ship girders in ways other than on trucks, barges. You can see here, one does have to be careful when loading a barge, however, because that is a fluid situation, literally. And if you were to load it up asymmetrically, the barge begins to move asymmetrically and may do things to your load that you weren't intending. So that's not a designer's problem, but that is an issue that fabricators or contractors need to be aware of. I've actually been on a job where girders disappeared off of a barge because a contractor unloaded them asymmetrically. When the girders are being erected, they are typically lifted by 1 or 2 cranes. You can see that here in a couple of photographs. This is that really long girder again, not in Washington, but in Canada. You can have 1 crane pick it up. Here there's a spreader beam to keep the angle change in these in the cables from being too extreme and introducing too much compression into the girder. Here you can see a single crane pick where it's short enough and they have long enough slings to keep that angle reasonable. Something that's sort of interesting to me, I like showing these pictures, is that in some cases, and I know up in the Northeast, they've used these some as far as launching girders, where you put a girder out in place. It's a fabricated steel unit typically. And the crane picks the girder up, sets it on a trolley that's mounted on that launching beam, and then the truck backs up to push the girder across whatever it is that you're spanning. And then there's another crane on the other side. So you can minimize the size of the cranes that are involved by each of them pretty much just having to do a vertical lift at the ends rather than having to span out over the creek or whatever it might be. Pretty clever idea. It works well. And this is one that I got some pictures a couple of years ago. Talk about launching beam on steroids. This is just for fun. This is in Oregon. You can see there's one of the girders going across the launching beam. Here you can see the truck backed up and positioning, the crane positioning the end of the girder onto a trolley on the launching truss or beam in this case. So the truck is then going to back up, pushes it on, it gets to the other end, then now you have a crane on both ends. But I think what they're doing here is they're repositioning to bring this trolley back under this end. And these trolleys are actually motorized. So they're actually driving this girder across the launching girders to get down to the other end where they have a couple more cranes. There's a crane down in the bottom, and then there's a crane up in the top that can reach this other girder. These photos came from the late Dr. Keith Kaufman with Knife River, just a really outstanding fellow. And they did some very innovative things out there in Oregon. And he was behind a lot of that. Something else that can be used is what's called a load triangle. And you can pass the load between 2 cranes. Here you can see the load triangle. You see that the load is going straight up into that sling, but there are other slings that are attached. And what happens is, here they're attaching it to get it off the end of the girder, or off the end of the truck, and the truck is backing up. So this crane still has it hooked on, but then this other crane is also hooked on. Now you can see that the triangle is pointing straight down. So that means each crane is lifting about half the weight of that girder. So they move it across till they can do that. And then the crane slowly switch loads until the one on the far side picks up the full load. The near crane unhooks, and then they can go ahead and set the beam. Here you can see the little bit of a close-up where they're currently sharing the load between the two ends. And a few last comments here. Occasionally we'll use shoring under girders. We don't need to use it a whole lot. It's typically if you're doing it for spliced girder construction, or maybe if you have an integral cap. So here you can see the shoring, which is typical. Here's some more shoring, a temporary tower for a spliced girder construction. And we also occasionally use strong backs. So this would be the navigable waterway or the main obstruction where you don't want to put a tower here because it would interfere with waterway traffic or whatever. So you put a tower here, tie this pier segment down, and use a strong back that's typically attached to the drop-in girder, and you simply drop the girder in and then it reacts on top of this pier segment. But you've got to have this thing tied down in order to do that. So really our keys to economical pre-stressed concrete bridges is to understand production and really take a careful look at design and detailing. We want to use locally available products. You know, we can't use cross sections necessarily that they're using in Washington State because we don't have the forms around here, but we have similar ones. We want to have repetitious use. We'll talk more about that later. And we would strongly recommend open communication between yourself, the designer, and local fabricators. And here we'll finish up with a pop quiz with a photograph from Dr. Keith Kaufman. Again, you see these guys struggling with a girder while they're erecting it. It looks like they're trying to keep the thing from going somewhere. So what in the world? Why is this happening? Think about that for 5 seconds, and then I'll give you the answer. What is going on is that this girder is being erected on a slope. And apparently the slings are the same length. So when they set the far girder, the far end of the girder sat on the bearing, this one was still off the bearing. You can see that there's quite a slope on this lead on the crane. So that means that this is pulling the girder in the other direction. It's pulling it toward the far end. So that's what's going on here. They are getting to struggle with that. So that's just sort of a gee whiz. I never thought about that. You know, here you can see it. They're setting this down and it's not down over here yet. Not anything we need to worry about as a designer, but it is something that happens that the contractors need to think about. Just a gee whiz. Give you a little something fun to think about as we wrap up this section. So now we are ready to move on to Greg Gorman giving us a nice presentation on his plant and some of the products and all that they have. So a virtual plant tour. So I will let you take it away there, Greg.
Okay, thanks, Reid. Don, I know there were some administrative type questions already this morning. I don't know if you want to take a minute or two and address some of those verbally before I get started.
Sure, we could do that if you'd like. Or, oh, you're saying if Don wanted?
Yeah, Don,
Yeah,
there were some questions about downloading some files and PDHs and things like that.
Yep. So, and the other questions, we'll have JP and Reid field those. So thank you for submitting those. So folks, we recognize it sounds like a couple of the DOTs, the Dropbox is blocked. So Reid Castrodale in the chat function provided a WeTransfer link. So if that doesn't work, let us know, because we could try to upload the handouts, but they're very large And so we really didn't want to do that in the chat function. We could do that, but it would probably clog up your system. And I think the WeTransfer, we're hoping, will be the best solution. A couple of the files aren't as sizable, such as the PCI transportation, the new catalog, as well as the producer matrices, product matrices, so we could upload those, but just let us know. We have the participants. Please, the folks that aren't muted here, but let us know in the chat. And as far as reporting your information to our education director in Chicago, and they forwarded on to rcep.net, your when you logged into Zoom, we have the time that you logged in and the amount of time that you were on the call. So that will, of course, equate to your personal development hours. That file with your information will be reported so that you get your credits. Okay. Hopefully that answers some of the basic, some of the questions we had early on in the seminar. And the other technical questions, we're saving those for the Q&A portion of the seminar. I know JP has been logging those. So with that, Greg, I'll turn it over to you for the virtual plant tour.
Okay. Dan, just to make sure I'm on the right screen here, are you seeing the one that's pre-stressed concrete bridge design?
I can see it.
Okay, good. All right, so the only thing better than a virtual plant tour is an actual plant tour. And I'll talk a little bit more about that at the end of the presentation. But today we're going to see some production processes, some of the products that a lot of us producers make, and then some of the projects that the products are going into. There will be a little bit of duplication from some things that you've already seen with Reid, but that's okay. So this will be a pretty brisk walk. So buckle up and here we go. Our plant in Roaring Spring, Pennsylvania is about 250,000 square feet of production space. There's 7 casting beds and shops, steel shops and carpentry shops, and some in-plant offices and kind of all the above. It's always good to have a young engineer in your office that has a drone, because you get cool pictures like this. This is our plant from aerial view, and you can see a lot of things, typical to most plants. There's a loading area just to the left of the facility, and storage yard where we store a lot of our product. And in our case, we have New Enterprise has a quarry at the top of the screen. It's right next to us. Well, it all starts with the engineering. If you don't get that right, it seems to follow the project. So it's extremely important to get that right. A lot of producers these days are using 3D BIM technology. We've been using Tekla by Trimble now for several years. And here we see the guts of a adjacent box beam. So you can see all the reinforcing steel. You can see the post-tensioning ducts and the lifters and also the parapet steel. And same thing for a bulb T. One of the big games that we've experienced with using 3D is no longer can you draw 2 things that occupy the same space. So we've had a lot better quality drawings down in the plant, a lot better fit up, and that kind of relates to a lot better fit up in the field as well. This is a stair tower and a parking garage, but we just kind of threw this in to give an idea with 3D how visual it is and how you just really get that visual gain, but also with the information that comes with BIM. It'll do things like you see all the thin brick that's on this garage, and it'll do counts and takeoffs for that as well. Just a typical model of a total precast bridge. You can see the precast footings and abutment and wing walls, pre-stressed ball T-beams and approach slabs, and the precast deck modules with the integral parapets. So I showed this one. Now this is actually a total precast bridge in Lehigh County over I-78. But the other thing that is just really super that you get with building information modeling technology is you get an immediate count. So I bring this up and I can know that I have about over 180,000 pieces of rebar and hardware in this structure, and it's all itemized. So a lot of value in what the power of what BIM can do for you. Just another skeleton of another bridge. This is one of the Berks County underclearance total precast bridges in Berks County over I-78. I throw this in. This is an example where we have a model. This is a walking bridge at a local amusement park, but you get to see model to actual, and just really to kind of show the architectural aesthetics that we can do with precast. The original owner of architectural precast in Middleburg, Pennsylvania, Bud Mattern, he made the statement that if you can draw it, I can cast it. So there's a lot that can be done with a lot of different geometry and finishes. Most plants are set up, in production functional areas, maybe not exactly as I'm showing here, but probably similar. The first thing is safety. We work around some huge, unforgivable forces every day. And just looking at all the stuff that Reid was talking about with the pre-stressing and just the weight of the pieces and all the cranes and equipment, there's a lot of forces. So safety is paramount. And quality control, PCI certified plants have a cache of PCI certified, usually level 2 and 3 quality control techs. Production control is where we do our scheduling and material acquisition. And then our direct, boots on the ground production areas with supervisors. We have our shops areas, our plant production, which is the bed casting areas, batch plant, and yarding where we store product. So kicking it off with the batch plant, the mixer is a planetary countercurrent mixer. And you see the silos in the control room and the buckets. One of the advantages that Reid mentioned with plant cast, precast products is you can see all of this is inside. Most plants, where the elements can get extreme, especially in the wintertime, will have at least part of their plant indoors. And there's a lot of environmental control with that. That helps with the quality of the concrete. This is an example of an abutment wall. This is called match casting. So at the top of the screen, you see it's a corner column for a total precast bridge, and the abutment wall is being cast up against it. So that acts as a form, and it's called match casting. So you see the setup here with all the reinforcing. You can see the post-tensioning ducts. And on the left of the screen, you see the splice sleeves. These are NMB splice sleeves, and that's a very common connection between wall to walls if they're stacking, or certainly wall to foundation. An abutment wall setup, you see the forming. Couple things to note here. There's you see the shear key to the left for the connection to the adjacent wall. And on the bottom, you see a form liner. This is an ashlar stone form liner. And form liners are a relatively inexpensive way to get some really nice aesthetic finishes. This is the abutment wall with all the steel. And it's ready to cast, ready to pour. And it's actually probably the wall that's on the bottom of the stack. But these are, the abutment wall stored out in the yard. In the top piece to the left, you can see the NMB splice tubes. This will likely go on a foundation. Footing setup, ready. Actually, we started to pour this one already. You can see the concrete in the bottom. And you see the vertical epoxy coated rebar. those will be the bars that will go up into the splice sleeves to make the connection for an abutment wall or a wing wall. And this is the footer completely cast and detailed and ready to get loaded up and head out to the yard. This is an adjacent box beam. It's a fascia beam and set up with a form liner, architectural finish. It's set up, getting ready to get the forms on and pour it. And this is the piece completed. So you see kind of a unique form liner finish on that. And this is detailed and ready to take out to the yard. Most fabricators are going to have a decent sized carpentry shop for making formwork. And also a steel fabrication side as well to fabricate all the reinforcing. And then once the parts and pieces go through the shop and they're fabricated, off of the shop tickets, they're organized in these racks and ready to send out to the particular casting areas. This is another quality control function because these pieces are all, numbered exact. They don't make extra pieces anymore. So if you have extra pieces left over when you set up a beam, either they miscounted in the shop, which they rarely do, or you're missing a piece somewhere. So it's kind of an additional quality control check. We're going to walk through the setup of a bulb tee and then also a box beam. So this is we call it the pallet liner. Another term for it is soffit. You saw that in Reid's presentation. But the beams were just stripped off of this from previous day pour. It'll get cleaned and oiled. And then we'll put some plywood down on top of the liner and pull the strand down the length of the bed. And it's important to get the plywood there because you don't want to drag the strand through oil because you need to have that strand bond for your pre-stressing. And here's a single strand jack. We saw one of those in Reid's presentation, and you can see all the strand in the background in the coils that he talked about. Here's a single strand jacking operation for pre-stressing. And this is the dead end. We refer to the other end as the live end. This is the dead end or the anchored end. And this is another example. Reid had talked about a multi-tensioning system or device. And this is one of those. And so sometimes precasters have those or the single strand. And this is the live end of a bulb tee after all the strand has been stressed in the stress blocks. And some of the stress blocks like Reid had showed are plates, and sometimes they're just set up with all the holes like these are. And you can see at the live end, there's some of the quality control markings to be able to go back and check for slippage. And if we could see a little bit more of the strand, you might see some marks for checking elongations as well that he talked about. Oftentimes load cells are used at the dead end, and different customers have different requirements for load cells and how many are used. But typically, two functions: one to verify your pre-tensioning forces, but also to check for slippage, especially if you're going to have something that's going to be set up for any length of time. It's something you can go back and check and make sure that you don't have any losses. So this is a same bed, and it's set up with draped. Now these draped strands are referred to as draping. I've heard harping. I saw that in a couple places in Reid's presentation, or deflected are some of the terms that are used for it. And this is, I think I saw in one of Reid's slides, he called this a harp horse. But he also did call it a hold up. So especially at the ends of the beams, and if you're doing more than one beam to a bed pour, you need to have a hold up in the middle for the draped strand. Okay, this is the beam with all the stirrups and I call them top racks installed, and you can see the draping in the middle of the beam. And then tying in the end steel as well. This is an elevated rack in one of our larger beam casting areas. So when you get, some of the taller eye girders, the racks get pretty tall. So this is an elevated rack tying station, centrally located. This is in the one of our box beam bays. You can see the rack tying station in the background. One of the racks, or a couple of the racks just off to the left. And then the example of one of the skids coming in from the shop with all the pieces organized and marked, ready to put together. Here we have a bulb tee, pretty much tied up and ready for forms. You can see at the front end the diaphragm inserts and all the strand stressed, and then the forms go on. And box beam, same deal. So all the parts and pieces for a box beam ready to go into the casting area. So we call the end form of a beam. This is two ends of two separate beams. We call that a bulkhead. You see the strands that are going through, and there's some styrofoam pieces as well. And what that does is it leaves kind of a section out where we can go back and burn those strands back and then patch the end of the beam. Here's the voids going into a box beam. The bottom steel's already in. Voids will go in, and then the top rack will go on top and tied in, and then we pour the beam. You see the throughout the top of the beam, the vertical bolts with nuts on them, and then off to the side there's C clamps, and that's a hold down system. So there's a tremendous amount of buoyant force with the styrofoam voids. They want to come up out of the beam when you start pouring it, so those need to be held down. And then some finishers finishing the top, putting in the weld clips and making sure that they're in the right place and doing the finishes on the top. Quality control from A to Z, beginning to end. Level 2 and 3 PCI certified, and just checking everything. On most DOT projects, there's a third-party quality assurance inspector as well. So a lot of quality inspection in a plant. Most fabricators will have some form of a database system, and we saw some of that in Reid's presentation as well. This is a beam ticket. It pretty much, with the database system we have, it tracks everything cradle to grave with every piece that we make. And our system's called Beam Tracker. And but anyway, this is one of the tickets that it spits out for a piece with a lot of information and checks on it. Testing areas can be in the bed casting areas or centrally located by the batch plant. We kind of have both. And this is where all the wet testing is done. If it's conventional concrete, slumps, SCC concrete, flow, air testing. And we also make our cylinders here and have our universal machine for braking to check strengths. Here we're pouring a next beam. And the same next beam, this is the curing. We cover it up, and this is steam cured. So some customers allow you to take the forms off of a piece before you reach your release strengths, and some don't. But once you get to that point either way, if you're required to get release strength, after you get that, you remove the forms. And then you detension. And so when Reid was talking about the detensioning and then cutting of the strand, or burning of the strand rather, you see there's a quality control tech off to the right, and she's got the burning sequence. So that's the insurance. We have either a supervisor or a quality control tech at each station when there's multiple beams to make sure that they're cutting the same strand at the same time. And these are what the beams look like when they come off the bed, and they go to the finishing area. And when we're done with them, they look like this. And we have a system we call green dotting, which when it's green dotted, it's ready to go out and be stored in the yard. Kind of threw this in just to see a little variety of some things we could do with precast. This is actually a prison cell. You see the form in the background and the rack in the foreground. And this is a precast cell module. It's 2 cells. It's a 15 by 15 and for 4 inmates. But anyway, just kind of throw that in to see a little variety. Some of the projects that our precast pieces go into, there's Eagle Stadium in Philadelphia. This is a parking garage in Norristown, Pennsylvania. I throw this in just to show a lot of the finishes with different brick and cornices and all kinds of different aesthetic finishes that you can do. And I realized that this is more of a transportation seminar, but it's fair to show a parking garage because we just erected one for District 6 PennDOT in Valley Forge, actually not too far from that garage. This is actually an 8-level total precast building, but it's an 8-level correctional facility in Toms River, New Jersey. Again, this is Lincoln Financial Field in Philadelphia, about 4,000 pieces of precast. The Pagula Ice Hockey Arena up in State College, Penn State. And a lot of industrial buildings as well. This happens to be a bus maintenance terminal in Johnstown, Pennsylvania. These are some pretty large insulated wall panels with architectural finishes. But there's, from an industrial building standpoint, schools, data centers, warehouses, a lot of facilities. And then, of course, prestressed girders and other substructure pieces. This is the a splice girder system, cantilever drop-in. It's the Coplay Bridge in Lehigh County. And Northeast Prestressed Products fabricated and delivered this bridge system. And this is total precast bridge. And this is one of the underclearance bridges in Berks County on I-78. Some of the products that we make, ash toe girders, truss beams. This is one of the Coplay haunch girders in NPP's plant. On the left, you see it pretty much totally set up. Not a tremendous amount of pre-stressing in the bottom, but you see the post-tension ducts coming out in the center of the girder. And then you see the forming on the right-hand side. And there's the beam after the forms are taken off. So with haunch girders, there's a lot of, it gets tricky handling and storing. You have some, different other than normal considerations. The haunch section in the middle, I want to say these are probably about 10.5 feet deep, or possibly even 11. So that gets pretty deep. Then there's bulb tees. Prestressed piles. This is at Atlantic Metrocast in Portsmouth, Virginia. Bed set up for pre-stressing piles. And another pile of piles. Adjacent box beams. We know these are adjacents because they have the shear key on the side, and you can see the post-tension ducts. And spread box beams with a little bit of a skew. Slab beams. And some next beams. These are kind of like parking garage double T's, but the vertical stems are much wider. They're kind of like on steroids. With accelerated bridge methods, there's a ton of different things and varieties. This is an example of some pre-stressed bulb tees with precast decks. And you see the hoop steel coming out the sides. And so that's that'll be a closure pour in the field, typically an ultra high performance concrete closure pour. This is a modular section, two kind of heavy, two spread box beams with a precast deck. And also we cast precast decks on steel girders. In this case, it has an integral curb for guide rail. Sometimes you have the whole parapet. And then just a bunch of parts and pieces, substructure elements for total precast. Here we see pier sections and footings. Here's some abutment caps and pier caps and columns. Again, more footings and deck slabs, pier sections. You see they're match cast and will be post-tensioned together. Approach slabs with integral parapets. Wing walls with architectural form liner surfaces. More approach walls with integral parapets. Bunch of deck slabs, and you see with the deck slabs, the openings in the tops of the slabs for the composite steel of the girders that will be underneath. And a whole bunch of substructure pieces of for a total precast bridge stage to do a dry fit. These are fascia beams with ornamental parapets casted on at the plant. Match casted retaining walls that get post tension together. And just a bunch more commercial products. This is for mostly for a parking garage. You have some light wall, double T's, inverted T beams, and then to the left you can see some beams and deck slabs for some bridge work as well. So a little bit about yarding and loading. Take some pretty sizable specialized equipment. Here we have some travel lift cranes taking an ash tow eye girder out of the plant and taking it out of the storage. And here we have a next beam getting stored. And this is a dry fit setup. So we got the foundation footing pieces all set up. You see the vertical rebar and then the abutment wall sitting down on top of the vertical bars. And you can see in the bottom of the abutment wall all the holes for the splice sleeve. So those are the grout tube holes. When they get grouted, you pump the grout in from the bottom until it comes out to the top, and that makes your connection. So again, just dry fitting a wing wall. Pretty heavy piece. I mean, this is about 3 foot thick. And then delivery and erection. So here's some of the specialized equipment that Reid was talking about. This is an 8-axle steerable, and he's right. It's not just anybody can jump in a truck and take off with a super load on one of these. So you have the driver that's steering the front of the truck, obviously, but also the rear when it's not tracking. Lots of times when we're going around tight turns and going through towns and things like that, we'll have spotters as well, and also at the job site. So a pile of super load beams getting ready to launch to a job site. And here's the haunch girder that MPP is delivering to the coplate job. So again, some extra considerations because of the depth of the middle of the haunch. Okay, I'm going to show a quick video. It's actually going to be it's a project in Maryland delivering 10 super load beams. And so Reid had talked about the launching girder, and we're gonna see that. So the project manager for the owner on this project put a GoPro camera on our beams as they were heading down the road. So anyway, it'll be a brief video, but you'll get to see the hauling. You'll be able to see the skid beam and the cranes lifting and skidding or launching and then setting the beams. Project site. So first beam. And no trees were damaged in the making of this video. Just a couple utility poles. So a lot of traffic control getting through some of the turns. Out to the job site. You see the launching beam there to the left. And so we'll see the crane's going to pick up the one end, set it on the launch. The truck will back it up, and then the other crane will pick it and set it. There we go. There's a spotter. All right. And then I have a short video. This is a pile driving operation. It's not at a bridge site, but same operation. Okay. Then this is a total precast bridge going up, and I think this is the Lehigh County project. And they're setting a deck piece on the bulb tees. This one happens to have an integral parapet as well. And the coplate job, you can see the shoring towers that Reid had also showed in one of his pictures. But this is a cantilever drop-in system. You see the haunch girders on top of the piers, and it's ready for the drop-in beam. So here they're setting the drop-in. Okay, so that pretty much wraps it up for me. I just want to basically say, like I mentioned, when I started the presentation, the only thing better than virtual is actual. And I know before COVID, we've done a lot of plant tours for a lot of different organizations, colleges and universities, engineers, DOTs, banks. I mean, just a lot of different folks. And so there's nothing like, going through a plant and seeing, how we do the things that we do. So always invited. I think a lot more plants are opening to that now. And so if you're not close to a plant or not sure what plant you're closest to or have a contact there directly to request a visit, certainly get with Rita or Dawn, and they'll set you up with a plant that's close with product that you want to take a look at. So that's it for me. So with that, I'll thank you for your attention and turn the program back over to Reid.
Thank you, Greg. That was a great plant trip and demonstration and all that kind of stuff. That was really good. Appreciate you sharing that with us. And we'll be back here and get started on the last of the sessions. What we're talking about here is taking a look at some economical detailing and designing issues. We're just taking a quick sample of a few of the things that we as designers should really be taking a look at. And I guess I'm not sharing my video yet. There we go. That we need to take a look at as we detail girders. Chapter 4 of the PCI Bridge Design Manual does a good job of giving some strategies for economy, some geometry things. I'll hit on just one or two of those items. Then Chapter 6 also has preliminary design charts. It's a discussion, so there's some things that are presented, and then there are design charts for some typical standard girders as well. So I'd really encourage you to take a look at the bridge manual and look through these chapters, see what you can learn. There's some issues that we have to, as designers, think about. There's some span length versus structure depth and splicing beams to increase the spans. That's starting to happen like in Coplay, and then the picture that I had on my desktop, which is a bridge over the Christina River in Wilmington. There are approaches to maximizing span lengths, all these sorts of things that you can read about in chapter 4. But one of the things that's sort of interesting is skews and flares. And I'll just spend a moment taking a look at that. The PCI bridge manual has a detail here. This is coming from the bridge manual, which is something like what I had mentioned earlier. Let's see, let's just trim the top flange of a bulb tee if possible, or and also to keep the bearing pad square rather than skewing the bearing pad. And then there's an example here from a Georgia DOT detail where they're showing that you keep the bottom flange square, and then here's the trim to the top flange. And we can make that sort of thing work by detailing, but it is helpful. Keeping the bottom flange square is helpful for the pre-stressors, and then just having that limited trim of the top flange. What do we do if we have flared spans? I think engineers' knee-jerk reaction is we'll use uniform spacing at this end and uniform spacing at this end. Well, that means that every beam has a different length. That means all the diaphragm holes are at different places. So that is not the easiest thing to do for a pre-stressor. As we have mentioned a time or two, repetition is something that really helps to get economy going for a pre-stressor. So this is another solution where you keep most of the girders straight, and here we only have 2 odd girders that are a different length. So that is a helpful solution for a flared girder type situation. We also have details to take a look at as far as reinforcement. There are multiple pieces that we can use. Here's an example of some confinement bars. I think that we saw some bars in the pen stress slides from Greg that it's a single piece. I forget how it came down and then over and all the way around. So a single piece of confinement reinforcement, which is handy as far as layout and labor. But some details might show up like this. Well, each time you have 3 bars, it takes a good bit of labor to put them in. You have to put the labor in. You're also sacrificing some area by lap splices. So there's some trade-offs. And again, I would encourage you to talk to the pre-stressors. It's possible that you could have a single bar like this that's closed, but what that would mean, realizing what we're doing with pre-tension construction, is that they would have to thread all the strands through all of those bars. And that would probably be a complication they would rather avoid. So other details are typically used. So that's just some things to be aware of. Another thing that we look at here's some top flange reinforcement. And they have these bullhorn bars or whatever you want to call them that are sticking out, and you see the lap is going all the way across. What that allows is some tolerance in placement of those bars, because when you bend those bars, they aren't all bent precisely. So you have to be able to accommodate that, or if the bar is a little bit too long, then you're shorting your cover over the sides. So if they're 2 pieces, you can make them, the points end up where they want to be, but you've also sacrificed all that double steel across the top. So there are different ways to do it. It may be that in Greg's plant, where they're fabricating their own bars, they have really good control on tolerances, and they may be able to do this in 1 bar. And that's something to consider. Maybe we provide options as designers, either a single piece or a double piece bar, or the fabricator may come back with an option in their shop drawings. So we need to be able to entertain that and realize that's a good idea, or understand why they're doing it. There's a fair amount of non-pre-stressed reinforcement that we saw that was being used. One of the options for that is to use welded wire reinforcement, where all of these are panels. This is all panelized steel coming in sections, and you don't have to put it on racks and tie it up. You can just take that. But one of the things that for designers is important is that they need to have standardized panels. Every girder can't have different panels. We need to standardize our end zones, standardize out in the middle, standardize the top flange reinforcement, and even the confinement bars, so that we can use them over and over again, and they can order it effectively as welded wire. It's interesting to note, even these bars here that have the deformations, those are welded wire as well. You can get deformed wire up to a number 5 equivalent. You can get a D31, that's the area of the bar, equivalent to a number 5 bar. Now, these wire reinforcement bars are actually higher strength. They've been cold worked some, so they're up to 75 or 80 KSI. The LRFD spec allows us to use that in design. Some DOTs do and some don't as far as allowing that, so you need to check with that. One nice thing about welded wire is that the cross wires that you see, can't see any, there are a couple of cross wires here on this top flange. That's what gives you your development. And they are developed very well by those cross wires. So they can simplify some of your design. So I would encourage, and you need to talk to your suppliers first, but allow the option for some welded wire fabric reinforcement for girders. Here are some of the design charts. The PCI Chapter 6 Bridge Design Manual has a series of them. They have the cord slabs, they have box beams, they have AASHTO girders, and the PCI bulb tees. And that's really a good place to start if you're trying to come up with a preliminary design. They're going to get you in the neighborhood. The assumptions may be a little different, but you need to take a look at them, or they're helpful to take a look at. Here's an example of one of the charts you get for a beam family, and that is the maximum span length versus beam spacing for each of the different depths of girders. So this is a BT72. If it's spaced at 6 feet, you could get about 155 feet out of that. So that it gives you a good bit of information just to get started to understand what you might be able to do with the girders. We're going to talk about this a little bit in, I forget which day, I guess it's the second day, a week from today. We'll talk some more about the different girder sections. But here are some design charts for the New England bulb tee. And the PCEF girders should be pretty much the same as what you would pick off of these charts. These are available on the PCI Northeast website under the Technical Resources tab. So you can get the maximum span type of a chart that's here. And then there's also one that actually gets you dialed into number of strands and whether it's a high strength concrete or a big strand. You can pick that information out of this chart. One of the things that's very helpful is that we as designers should design or allow the option for same strand patterns if possible. We love to sharpen our pencils and try to use the least of everything. So we feel like we ought to be putting the minimum number of strands in every girder if possible, but that doesn't necessarily give the most economical solution. If your producers are putting multiple girders in a bed, they don't want to cast one at a time if they have to, and I'll discuss that a little bit more as why that would be required. It may appear that saving a few strands will help, but using the same strand pattern on several girders will will help out a lot in economy. And I have some examples of this. This is a single design where the designer used two more strands on the exterior than he did on the interior. So there's 52 strands on the exterior girders. So there are 2 of those, and there are 50 strands on the interior girders, and there are 5 of those. It turns out if you look at revising it, and this is a table that's giving us a summary, here is the exterior that has the 52. Here is the design for the original, for the interior, which had 50 strands. And then here is the revised design if we assumed 52 for the exterior girder. And you'll see that it actually, using the 52 for the interior, actually improves the stress condition, gets you farther away from your limiting stresses, and also puts you closer to having the same camber as the exterior girders. So it's showing us here that it would be really beneficial for the producer and for the design itself and the contractor if you were to use 2 more strands than this absolute minimum. Now, we did sacrifice a little bit in material. You see here that if you had the 2 at 52 and 5 at 50, you're going to use 354 strands. If they're all at 52, you're using 364 strands. So it's 10 more strands, and you're using about 2.8% more material. But it really depends on how the pre-stressor is set up. If you only had 1 span and they had a really long bed, so they'd like to cast them all in the 1 or 2 pours, it would be better to have all the girders to have the same number of strands. If there's just 1 span, maybe it would be better, maybe you could get away with this. It depends on their bed situation. So it's something that we as designers need to bear in mind. And if they propose something that we should be open to that, it really gives them the flexibility to set their beds up as they would like it. And then here's one that's a really rough example. There was a series of spans that used bulb tees, and then there was 1 trapezoidal span with opposite skews. So there are 4 girders in this cross section. This is using a type 3, so it doesn't, they're not using type 3s anywhere else on the project. So they have 4 girders that vary in length from 27.5 to 56 feet. And so the designer said, okay, well, I'll design each girder. So they had 4 different strand patterns, and the number varied from 10 to 20 strands. Well, this causes issues for a pre-stressor. And these are short enough girders that they're going to want to put several, if not all of them, in 1 pour. But if they all have different strand patterns, let's say you had a 300-foot bed, they all have different strand patterns. So you have to string that bed 4 times. So you have 18,000, almost 19,000 feet of strands, and it's going to require 4 pours. Well, option 2 might say, okay, can I use 20 strands on all 4 beams? Or maybe I use 2 strand patterns. Maybe I use 20 for 2 of them and 16 for the other 2, or whatever it might be. So maybe you could get down to 2 pours. A third option would be is if you cast all 4 girders in the bed, and maybe you used some similar strand patterns if you could do that. But something else that can be done is what's called full length debonding, where you're actually disabling the extra strands. So in this case, you'd be using about 1/3 of the strands of the first one. You're using 20 strands for the total length of girder. So you end up with 6,600 feet of strand, and it's 1 pour. It takes about 1/3 of the time of bed casting. So for this particular job, it was recommended by the pre-stressor that they would like to use the full length debonding option. But the fabricator had to bid it using option 1 because it wasn't in the bid documents that they could use full length debonding. So they could save 1,200 feet of strands. Well, the DOT allowed them to use the full length debonding because this is, I think I cover this in a couple of days, but full-length debonding is actually detailed as an option for the standard plans for cord slabs and box beams for NC DOT. So the fabricator knew that it was a good chance that they might allow it, but he couldn't bid it that way. So the DOT lost out on savings by saving 12,000 feet of strand and a good bit of labor. So that's something to bear in mind as we do our designs. And at that, there are more strands in this section, but I think that we might ought to cut it off here. I would recommend that you go ahead and take a look at the other slides because there are some more concepts that are presented about detailing of girders. But we'll stop here and go to the questions, or first we're going to go to Reid Castrodale to give us the PCI Northeast update. So take it away.
Actually, I think that we've had so many excellent submitted questions, and there are a wide assortment of topics there that Rita's presentation, everyone, is available in the handout section. And most of what she was going to cover was really reference tools. So Rita, do you want to jump on and just kind of flip through that quickly, and then we'll transition it over to Reid and JP. I know JP has been diligently monitoring questions so that we can answer them for our participants here. Thank you.
Yeah, I think what I'll do is I'm going to go through this relatively quickly just to show you what's in it. It's only a few slides anyways, but I just wanted to call your attention to a few items, and then we'll jump into the Q&A simply because there is quite a bit of number of questions, and obviously we're not going to get through all of them, but we'll try to get through some of them. But I just wanted to call your attention to a couple of quick items, which is the new transportation publications catalog that PCI literally just did last month. It has all the information related to bridge that you would really want to know. It has an extensive table of contents that will walk you through what's in the actual catalog. You can get to that catalog through PCI's website when you go to design and then to the transportation, click through, and then you'll see the actual catalog there. And again, if you are online, it will hyperlink to the actual document that you're looking at. So you don't have to kind of look at the catalog and then try to figure out how to find it. If you find something that you want, you click it and it'll bring you directly to the bookstore, and you can actually, download it for free if it's an e-copy. There are some e-copy that are actually you'd have to pay for, but most of them are actually free. And then you can actually get there through the publications tab from PCI's website, right directly to the bookstore. And I'm going to skip these because we're out of time, but I also want to call your attention to the e-learning center, where there are an extensive number of classes that you can take on demand. Obviously, Reid is giving you all the basics today, but if you want to go into more detail on certain topics, you will find that through this e-learning center. And then basically it is let me go move forward here. I think somebody was trying to click through. You can get there through the education tab too, but if you click on e-learning, it will show you the on-demand portal, which looks like people are still trying to get in. Yeah, screwing up the thing. And this is what it looks like. I just wanted to quickly show you. There's the classes, you can sort them, and then you click the one that you want. It comes up like this, you register, you sign in, and then you begin taking the class. It's a talking module. It'll last about 60 minutes. You can start and stop how many times you want. There are tests along the way. There is a final test in order to earn PDH credit, and you can download the PowerPoints to follow along. And then quickly, I'm going to skip my PCI Tech Committee update. But for those that know me, they know that there's a lot of resources on PCINE's website. And the thing I wanted to call your attention to is on the session 3, we just recently updated the next beam guidelines. A fair amount of updates to it. Mike Culmo on my committee will be going through those changes on the session 3. So I would encourage you to attend session 3 so that you could hear about those updates. And then also the other document that was recently updated was the full thickness deck panel guideline. That one also has, this is what the document now next beam looks like. The deck panel guideline that we just updated includes PT, non-PT, UHPC joint, normal strength joints, and longitudinal deck panels. So it will cover all the types of applications related to full thickness deck panels. And ABC, I'm going to talk a little bit about tomorrow. I'm going to skip this because we already went through it. Don will mention there's a brief survey at the end for those that leave, and that session 2 is next week, and then session 3 is the week later. So those same time slot. And so that was just a real quick like crash course in what's in that handout. But if you download it, it is self-explanatory. You should be able to figure it out. But we want to open up that Q&A period right now and try to get some answers to some of those questions that were in the chat pane. So Dawn, do we want to pick some questions? I'm not quite sure how you want to do this.
So JP, I know that you've been tracking those throughout.
Yeah, I've grouped them together, guys. So
Cool.
Great job, Reid and Greg. Greg, you might want to chime in on a couple of these. First, the first question that came in actually is about means and methods. So there's a couple in that regards. And just a clarification to caller Richardson, I think you meant the under ties for the girders. There's a question about bottom flange ties only at the ends of the girders. Typically, those are dictated by the form supplier. So I just wanted to clarify that. They're usually around 4 feet on center.
Unless it could be also confinement bars, so that you don't have to.
Oh,
I'm
it
not
could be
sure which
confinement.
way. Yeah.
Good question. Yeah. So some states require confinement only at the ends, and some require them full length. So that's just depending on the detailing.
Yeah. The specs don't require it full length, but some DOTs detail it that way.
Okay, great. So one question came in, Reid, about the purpose of the bearing plate. If the pre-stressed beam is supported by a rubber pad, for example, in an integral abutment, is the bearing plate necessary?
Well, it sort of depends. If there's a whole range of details that are used as well. Some states, especially if you have grade on a system, that if you just put it on a rubber pad, the thing will walk downhill. So it becomes necessary to have a masonry plate or something on top of it, and then anchor bolts to keep the girder from moving. So in that case, yes, an embedded plate is required to hold the girder, well, to attach it to the bearing, to the bolts, anchor bolts.
Okay.
And the other thing is just for production, that some producers would rather provide it during production so they don't have to patch spalls at the ends of their beams. There can be other details that can be used, and JP can address that better than I, but those are.
Well, you mentioned in skewed conditions, a bearing plate's always a great idea. Certainly can help. There's 2 questions about concrete. I think, Greg, you may be well suited to answer these. One of them is, how do we avoid segregation in the end of the girders with congestion of reinforcement? And then another one is maybe a little bit more specific. It's about potential cold joints that could occur, especially if there's a lapse in the pouring of the concrete. So I think maybe the congestion one, Reid, you could answer that. And then if perhaps the concern about cold joints was a very lengthy question, we might want to handle that offline. But
SCC or flowable concrete is typically used to try to get past all that congestion, because there is a lot of congestion, and those are some of the slides that I skipped. We as designers like to just say, okay, you have confinement bars. Well, they're lapping underneath the strands. So you have 2 bars for every one that you're showing. As far as you end up starting to build a little bit of a platform. You may have other bars that are sticking in at the ends. At any rate, it can get very congested. So it's very helpful to have a more flowable mix to get the concrete down, especially in that bearing and end region. And that's been allowed by a lot of a lot of DOTs, that they're allowing 9-inch slumps at the ends of the beams, or even going to full SCC where it's specified by a spread rather than a slump. You have anything else to add there, JP?
Well, external vibration does help a lot too. Sometimes with confinement areas, we'll try to increase the slump, whereas maybe towards the main span of the girder, if you will, we might use a lower slump. So you can kind of play with your admixtures throughout the span of the girder. But SEC is a great tool, and certainly one that more and more fabricators are leaning towards. Another question to means and methods is typically when raking the girder occurs for the 1/4 inch amplitude with SEC. That's a little more difficult, right? Because it's self-consolidating. More traditional mix, you can go right with a tine almost right away. So I don't know if you have anything else to add to that.
I don't have anything else particularly. I don't know if you have some more. I know that in some places they've actually used a textured, like a form liner or something to provide the texture because you couldn't rake it in. I don't know, but
Yeah, I guess the answer is when the concrete can adequately hold its shape is when you want to rake. So
if it's specified, the fabricator will figure a way and suggest it.
Here's a question. What is the typical release strength? Can we use 7,200 PSI? Can we use 8,000 PSI? I guess another follow-up question was, can you use 7,200 PSI if you have an 8,000 final?
I will be talking about that a little bit more tomorrow. That is a week from today. In that session, the encouragement that I would give is compute what you need and don't just use a number. Oftentimes what governs the concrete strength is the release strength. Even though 28 days is higher, you may get the 28-day strength at 3 days or maybe 36 hours, whatever. So we as designers shouldn't just pick numbers or shouldn't just say, well, I'm going to use 8,000 PSI, so I use 80% of that, and that's 7,200, and that's what I'm going to use. If you can back that release strength down, which can be back computed, you can compute a design and then figure out from the results to see what your maximum release strength is needed. Specify that, and probably use 100 PSI increments for your release strength, something like that. Don't round it off too generously.
Yeah, I think that's a great topic for our roundtable as well. A lot of the producers are going to have pretty strong opinions about that. Release strength really governs turnover rates on the bed, and 200 PSI, 100 PSI can take as long as an hour to wait for. So it can shift your production schedule to a whole nother day and a whole nother cycle. So Reid, you're going to talk about that next week, and then we'll certainly talk about it with the producer roundtable, I'm sure. Rita, did you have something to add?
Yeah, I was
Yeah,
going to say
that's
I concur, because the could really add substantial cost to a project if you just pick a release number and find out you just cause your project to go to a 2-day cycle instead of a 1-day cycle, and then all of a sudden the cost is a lot more than you anticipated, just because you just said you wanted it to be released at this strength. And the other big thing is that you're going to have, in order to get to that release strength, you may be looking at a mixed design that's going to have to be much more rich with cement, which means your concrete strength, final concrete strength, is not 8,000. It could be like 11,000 to get to that release that you've selected. So be real careful with playing with the release strengths, because it really could change everything on a project. So.
This question may be a little bit out of topic, but it is, what are some of the lessons that have been learned so far from design and fabrication of CFRP strand versus steel strand, pre-stress and post-tension members? Perhaps you could refer folks to your Aspire article, might be a good one to.
Yeah, there's a couple of articles in Aspire. There's also a CFRP guide spec that came out of an NCHRP project not too long ago. But there are some other resources. I'm not as familiar. I'm getting more familiar with CFRP, but and there's also the option of stainless steel strands. Those are coming out now too, and they have some differences. All those materials have differences in design. So we have to modify our design processes in order to use those. It's not just a one-to-one swap.
Sure. We could easily spend a half hour on that topic. I think it's certainly an interesting one. A couple questions about BIM. Was Tekla used for all the 3D models? I believe it was, Greg. You can chime in if it wasn't. And maybe actually, Greg, that might be just a good follow-up for you. There's two questions. Elaborate on the information that was given, and then I believe that was produced by Prestressed for their fabrication and the total precast. And the next one that came in was, what is the percentage of projects you use for BIM, and what is the net gain to making a BIM model?
Yeah, so first of all, yeah, everything that you saw in my presentation was all Tekla BIM. As far as what products, for us, it's 100%. Everything we do is in BIM. We do a little bit of outsourcing on the commercial side, but oftentimes when we outsource the engineering, although we have engineering in house, but when we do outsource the engineering, lots of times we will still do a model and do all the shop tickets and everything in Tekla in house. And then as far as net gains, so Tekla, to be completely honest, I mean, it's lots of the 3D BIM software applications aren't the simplest to learn. But once we've had CAD techs that start out in AutoCAD and transferred over, and in some cases it seems more simple if you haven't had the AutoCAD background and this is your first dance. But anyway, when they pick it up and start using it, I mean, the gains are you get a lot of gain in time. Models and things. So some of the models that I showed, only take like, an hour or so to put together to be able to go do a presentation. And you could take some of the, models that I had and you can spin them all around and look at them from every angle, but they're good for presentation purposes. But once you have your model set up, even if, whenever there's changes, you get a ripple, through your pieces and everything. But again, I mean, just in drawing errors and questions going back to engineering from the plant floor and fit up in the field with geometry. I mean, you just can't make a lot of the same mistakes that you used to be able to make in just 2D drawings.
That's great. All right, Dawn, you may be on mute.
Thank you. Thanks for that. So everyone, we had so many people. We have 450 people that are still on that we're slightly over. So we so appreciate your time today. We will make sure that we answer all of these questions, whether they're in written format, we send them to everybody after the seminar, but we will make sure that we answer all your questions. There have been a lot of questions about the recording. We will make the recording available to you, and we really appreciate if you complete the survey for us and let us know how best we can provide you other information, anything we may have overlooked. We would sure appreciate that. So we'll be sending that shortly as well. So thanks, everybody. We'll wrap up this session, and we hope that you can join us next Tuesday at the same time for additional topics. So thanks, everybody.
Thank you, everybody.
Thanks.
Thank you.
Thank you.